Dr. Bolong Huang. He is also from the Hong Kong Polytechnic University in the Department of Applied Biology and Chemical Technology. Dr. Huang has received his PhD in 2012 from the University of Cambridge and his bachelor degree in condensed matter physics from the Department of Physics, Beijing University. And he joined the Hong Kong PolyU in 2015, and now is the associate professor of the Department of Applied Biology and Chemical Technology. His main research fields are electronic structures of nano materials, energy materials, solid functional materials, and their applications in multi-scale energy conversion and supply systems. And without further ado, let's welcome Dr. Huang for the presentation. Dr. Huang, please.
Thank you. Thank you. Can you see the PowerPoint clearly?
Yes, we can see
Thank you. Good afternoon, everyone. I'm Bolong Huang from Department of ABCT. Thanks for kind invitation by the committee, Professor Raymond Wang, Professor Haitao Huang, and Dr. Biao Zhang. It is a great honor to join this important workshop focusing on the carbon neutrality technologies. Today, I will discuss our recent works in atomic catalyst design for energy system. First of all, I will briefly introduce the background of our research. Currently, the energy crisis has become the most significant environmental issue for the global community. The Hong Kong government is also currently focused on reaching the carbon neutrality goal in 2050. To achieve this goal, the development of green and sustainable energy system and energy technology is the key strategies. To achieve the carbon neutrality goal, the technology innovation in sustainable energy conversion system are important. In particular, the carbon dioxide reduction and fuel cells are the most important research fields. These electrochemical conversions all strongly rely on advanced and efficient catalysts. To achieve the practical application of this energy conversion system, the key challenge is the rational design of the electrocatalyst. Although the conventional noble metal-based electrocatalysts have shown good electroactivity, but the high cost and low boundness largely limit their large-scale industrial application. So in this way, we propose that atomic catalysts become the most promising solution for future energy systems. The unique electroactivity and atomically dispersed metal atom has been proposed for different reactions since 2003. In 2011, a single atom catalyst had been firstly synthesized by Chinese scientist Professor Zhang Tao's team. Since then, atomic catalyst has become the most frontier research topic. Recently, Chinese scientists also successfully realized the industrial applications of atomic catalysts. Compared to a conventional noble metal catalyst, atomic catalysts have several key advantages, including high electroactivity, controllable loadings, and low cost. Therefore, atomic catalysts have great potential in sustainable energy conversion systems. Reducing the size of the electrocatalyst from nanoparticles to the single atomic level will significantly change electronic structures. This usually leads to the unique electroactivity of atomically dispersed metal. However, due to the ultra-large surface energy of the single metal atoms, they often face aggregation issues during the synthesis. To overcome this challenge, the appropriate support materials are strongly needed to stabilize the single metal atoms. Currently, there are several main support materials, including oxides, metal organic frameworks, and carbon-based materials. Among all the carbon materials, Graphdiyne has shown significant contributions to different energy storage and conversion systems. GDY is an abbreviation. So GDY is promising support materials of atomic catalysts. Why? This is due to the intrinsic advantages of that materials in both the lattice structures and electronic properties. It has a larger specific surface area with naturally ordered power structures. And this has supplied a good environment to stabilize more single atom atoms. Meanwhile, it also shows a high electrical conductivity to guarantee the efficient electron transfer during electrocatalyst. Moreover, the remarkable chemical stability enables their applications under different electrochemical environments. For all atomic catalysts, the ambiguous valence states for single metal sites are the significant challenges. Therefore, the zero valence or the capability of maintaining that zero valence of catalysts have become the research focus of many scientists. However, only a few specific transition metal has been studied so far. And to address this challenge, we propose the new parameters, the Redox barriers, to screen the zero valence of SAC. Based on this model, we have globally searched all the transition metals and rare earth metals for their anchoring on the GDY systems. The electroactivities, electronegativities, and the stability of all atomic catalyst candidates have been compared. Through a detailed investigation of the electron transfer capability, we can screen out the most promising zero valence SAC. With the Redox model, we have also mapped out the energetic resolution of side-to-side charge transfer in two directions. This further facilitates our evaluation of the electron exchange and transfer capability. Meanwhile, the Redox model has supplied a way to accumulate rich parameters of different metals. The parameters obtained by the model can compatibly integrate with machine learning for screening. After detailed investigation, we have screened out that nickel, platinum, and cobalt are the most promising candidates for zero-valence GDY single-atom catalyst systems. To verify our theoretical exploration, we have further collaborated experimental groups from Professor Li Yuliang's group. For example, we have successfully realized zero-valence nickel and iron SAC on the GDY support. And this GDY SAC also shows superior performance and stabilities and for the hydrogen evolution reactions. Based on the optical stretching algorithm, we identify the closed shell effects of the metal due to the strong interactions with the support. This is the key to realize the stable zero-valence atomic catalyst for broad applications. So these results are also consistent with our previous theoretical screening and mappings. Another example of the platinum-based atomic catalyst on the GDY. In this catalyst, the zero-valence platinum is activated by the PD coupling by the orbital coupling with the GDY. As we predicted in our previous work, these electrocatalysts has shown excellent performances in the water splitting. And therefore, this investigation have confirmed that the potential of a theoretical screening of a SAC are consistent with experimental verifications. Then we move on from the zero-valence SACs to SAC with specific functions. And hydrogen has been considered as the most environmentally friendly and efficient fuel. Therefore, hydrogen evolution reaction, HER, has become the most promising method to efficiently generate hydrogen fuels. For HER process, theoretical calculation usually only compared proton binding energies as the only criteria for HER. In this work, we have extended such criteria to both initial binding of the protons and desorption energies of formed the hydrogens. It is noted that the 3D transition metal showed relatively lower energy cost to support higher electroactivity for HER based on the energy cost. And iron, cobalt, nickel, cadmium, platinum, and platinum are the most promising selection for HER. For current research on atomic catalysts, rare earth metals have rarely been discussed and applied. In many electrochemical reactions, the high electroactivity of lanthanide-based materials has been proved. Therefore, we have also introduced similar strategy to evaluate the lanthanide-based GDY-SAC for HER first time. Interestingly, it is noted that the lanthanide-based GDY-SAC show even smaller energy barriers than the most transition metals. Through the energetic change, and we found the Sumerian and European showed superior HER performance due to the smallest energy cost for the rate determining step. The active sites of a single atom catalyst system are usually considered to be the metal sites. And this is the problem. However, through the atomic resolution of the active sites, we have supplied different possibility of active sites. For the HER process, the alkaline chain in the GDY is the real active site or real active region rather than atomic dispersed the metal sites. It is found that most metal sites may cause the overbinding effect of the proton and the lower HER performances. Meanwhile, we have also determined that the rate determining state of the HER for GDY-SAC is the Tafel reactions. Due to the large barrier of RDS, most 5D metal cannot realize the efficient SAC for HER process. Then we further introduced the machine learning techniques as an individual method to screen the electrocatalyst. We have built up the parameterization database based on the Redox barrier. With this strategy, we have screened out the promising catalysts for the HER-based binding energies. The screening results are highly consistent with DFT calculations, and this confirms that the combination of DFT and machine learning can be a promising strategy for investigating novel functional materials. Beyond a single atom catalyst, the further steps towards the dual atom catalyst can supply more flexibility and possibilities. Introduction and additional of metals can enable more electroactivity modulation for different actions. However, due to the strong repulsive force induced by DD orbital couplings, the successful synthesis DAC is still very limited and challenging. In most cases of a dual metal site needs to stabilize through the additional oxygen, nitrogen, or carbon connections. We propose that introducing the lanthanide metals can be a promising solution for the first time. The FD coupling can induce a self and electron balance effect to alleviate the repulsive force for the stable DAC system. To find out the promising dual metal combination for experimental synthesis, we have investigated all the DAC between the transition metal and the lanthanide. As we expected, most GDY and DAC are not stable due to the large energy barriers, especially between the combination of the transition metal. In comparison, the combination between the lanthanide and the transition metal has significantly elevated the formation energy. So therefore, the hetero coupling of GDY DAC are most energetically favorable. Meanwhile, the modulation of electronic structures are also investigated. We found that the transition metal combination will not change the D-band centers and trends significantly. As the D centers increases, the D-band center shows the downshifting trends. So, however, the introduction of lanthanide metals shows significant perturbation to the electronic structures. The heterocoupling DACs display the evidently different D-band centers regarding the both evolution trend and range. To further understanding the electronic structure, we have also reviewed the F-band center variations. The F-band center of lanthanide shows a V-shape change, so the middle lanthanide metal shows the lowest F-band center. Compared with the D-band center, the F-band center is more sensitive to the second anchoring metals. Due to the FD orbital couplings intra-atoms and inter-atoms, the electron can be transferred from the D-band center to the F-band through the cell balance effect. And this effect can further optimize both electronic structures and thermodynamic stabilities. Meanwhile, we also carried out a parallel machine learning screening out the GDY DACs. And through this fundamental chemical physical property parameters of GDY DAC, the thermodynamic stability can be predicted with high accuracy. In comparison, due to the underlying orbital couplings, some electronic structure cannot be fully reviewed. This leads to the challenges in predicting the F-band center accurately. And this is also the first time we introduce a cell validating effect into the machine learning combined with DFT techniques. Recently, carbon dioxide reduction has become one of the effective solutions for carbon neutrality. In our recent work, we proposed GDY single atom catalyst system for the CO₂RR for the first time. Depending on the GDY platform, we have established over 5,400 models to carry out the comprehensive study of the CO₂RR, especially focus on the active site, the neighboring effect, and the selectivity in the special 3D special regions of the C1 products. The electron configuration of the d orbitals have shown important influences of the CO2 absorptions. Before the D6 filling, and the transition metal prefers the physical absorption by the docking effects with the empty d orbitals. This usually leads to the overbinding of the CO2. In comparison, the transition metal after D6 prefer the absorption of the CO2 with a suitable binding strength. Meanwhile, we have reviewed the selectivity of all C1 carbon-1 products through the comprehensive reaction pathway mappings. Most transition metal SAC prefer the formation of carbon monoxide when competing with the formic acid. In comparison, the lanthanide SAC can generate both products actually. We have demonstrated that the carbon CO2 absorption is more favored on the carbon chains rather than the metal acids. And however, during the catalysis process, the metal SA single atom sites display much smaller energy barriers. And this suggests the migration of carbon dioxide molecules during the electrocatalysis. For the more complicated carbon-1 products such as methanol and natural gas, the lanthanide, SAC are the promising electrocatalysts, especially the GDY, parasodium, and the parathenium SAC. Our work has confirmed that both the thermodynamic and spatial factors are significant for electroactivity and selectivity. Besides the GDY support, we also investigate the rational design of atomic catalysts in other supports actually. For example, the nitrogen-doped carbon materials, the iron 3D orbital demonstrate strong electron exchange and transfer capabilities. Especially for the PD coupling, it is the key to introduce the strong interaction with the support. This leads to the optimization and electronic structures. Meanwhile, we have also applied the orbital peak modulation strategy to improve the overall kinetic rate of the ORR process, which is collaborating with the Changchun Institute of Applied Chemistry of Erkan Wang's group. On the nickel cobalt oxide support, electroactive region consists of iridium single atom and a nearby oxygen vacancy. And this electron-active region has stabilized the intermediates and the balance of the surface cobalt sites. And these optimizations guarantee the optimization of the OER performances. Recently, our collaboration with the Nankai University has proved the feasibility of lanthanide-based DAC. In previous slides, we have shown that the lanthanide mixed with the transition metal are the optimal combinations. Actually, in this work, the zinc lanthanide DAC has really shown the two individual metal sites of the CO₂RR and HER respectively. By adjusting the ratio of these two sites, the corresponding components of the syngas can be modulated in a large range. This work further supports our predictions for high electroactivity and stability of lanthanide-based DACs. From the first step, from theoretical to the second step, now the verification by the experiments. Finally, we will also discuss the atomic level modulation in transition metal-based electrocatalysts. In recent years, the atomic scale engineering of electrocatalysts has gradually attracted electron and electrochemical research interest. In particular, the string effect has been widely observed in the transition metal-based nanoparticles. However, in the homogeneous work, we haven't done so far yet. So the conventional idea, the tensile strain upshift the down D-band center and the compressed strain downshift the D-band center. However, the answer is not. In the most typical homogeneous electrocatalyst, we discover that the irregular D-band center change induced by the strain effect. Through the theoretical investigation, we found that the strain effect is oversimplified based on all previous work. We found that both geometry and electronic factors are very important. For the geometry factors, the D-band centers show strong correlation with the interlayer bond length actually. This represents the detailed lattice structure relates to the electronic structure, which is potentially consideration for future discovery. Meanwhile, we have identified the new parameters, which is we call the surface atomic density, to describe the surface energy and electroactivity both. This parameter can overcome the limitation of the element selection and the morphologies. This surface atomic density linearly correlates with the phases with surface energy and electroactivity. With new parameters, both homogeneous and heterogeneous catalysts in any morphologies can be quantitatively modulated. And this work has been perfectly done by my students Wu Tong and Mingzi. And for the high entropic alloys, the surface atomic density shows the varied influence on metal alloys and high entropy alloys. It is noted that many alloys mappings show the 3D volcano trends. This indicates potential opportunities, rational design, and modulation of the novel electrocatalysts. Especially for the electroactive high index phases, the intrinsic instability has become challenging for many catalysts, especially for metal systems. By introducing the second metal, we propose that the structural change can be quantified by the structural entropy. And such a structural entropy, this concept, can further correlate with the surface strain effect in the surface atom migration and the surface reconstruction both. Therefore, this will propose the new direction to understand the strain effect and from the atomic level modulation in electrocatalysts, which is within the homogeneous atomic catalyst region. The evolution of high index phases homogeneous catalysts has been another important challenge. This is critical to the phase control in transition metal-based electrocatalysts. Therefore, recently we have studied the high index phases of several key transition metals. We are able to unravel the characteristic features of high index phases. And among this result, more importantly, the evolution of different phases and the pathway of SCC to the HCCP switch are identified. They are choosing the unique pathway instead of a random and disordered ways during the phase change. And then we further choose the representative late transition metal to investigate 100 towards 544 surfaces. We have simulated the experimental size nanoparticle and demonstrated atomic string distributions. Different from the lattice string, the surface atomic size string is the intrinsic features of nanoparticles. This distribution and the levels of the surface atomic string are determined by elements and surface structures. In particular, the surface steps and king steps with low coordination shows compressive strain. These size are key factor to modulate surface electroactivity, which is also can level up the at least one order magnitude for estimation of the active site densities given reference for experimentalists. To understand the electroactivity to high index phases, we correlate with the surface atom strain with the key intermediates of CO₂RR. It is noted that the same metal has shown similar absorption trends even for the different key intermediates. However, the absorption trends of different elements are independent of the phases. This work will help us to establish a theoretical framework for studying the high index phases of different nanomaterials. In the end, we will conclude our recent works in the atomic catalysts in homogeneous and also heterogeneous. For heterogeneous system for GDY-based atomic catalysts, we have proposed a novel Redox model and machine learning techniques to screen out the efficient zero-valence atomic catalysts for different applications. Also, for the GDY Dual Atomic Catalyst, the introduction of lanthanide transition metal combination is significant for both electroactivity and stability. Our proposed exploration strategies have also been applied in other atomic catalyst systems and the atomic level modulation of the nanoparticles. So in the future, we will keep exploring these fields and hope to realize the atomic advanced design for the atomic catalyst for more energy system towards carbon neutrality development. Okay, thank you. Thank you all for listening. And any question, I welcome.
Okay, thank you very much for the next talk. So now we have time for the question. So for the audience, you can unmute yourself, or you can type your question in the chat. So I'm asking simple questions.
Yes,
so,
please.
Yes. So here, actually, in the batteries, we want to do the opposite. Here, you want to catalyze the HER or OER reactions. In the batteries, we want to prevent the reactions. So do you have any comments if we want to prevent the HER or OER?
Thank you very much for your questions. And prevent, we usually introduce for HER system, we usually introduce the overbinding effects because we can screening out and classify the desorption and absorption range so that based on that level boundary, we can choose overbindings, especially in the electro range. And instead of the choosing electrolyte range, we will starting from the electro range. And in that range, we will build up this kind of a catalyst system to overbinding as long as even we generate HER process successfully, but however, the overbinding effect will stop that. So this is a proposed system. For OER, we also apply many atomic catalysts for ORR for metal air batteries. So this is can generate the ORR performance underestimated and overestimated. And based on overestimated, we can use this model to prevent this OER process. And this is for your references.
Okay, thank you very much. Because we in batteries, we're doing the opposite as in the catalyst.
Yes.
So this kind of gas generation is always not good to the battery safety.
Yes. And for these topics for batteries and electrochemical, I think in all the electrochemical range, well, our all topics are all connected. So it's just a different direction, one forward or one backwards. So we, as we just build up as many comprehensive as we can, so that we can choose the opposite direction to screen out the candidates for that prevent the HER and OER process and expect and support, give the positive support for these battery experimental experts.
Okay, okay. Thank you very much. So any other questions from the audience? You can turn on the audio or you can type in the chat.
Okay, Dr. Huang, may I ask a question? Yeah, see you. In fact, I also work on some lithium sulfur battery. For lithium sulfur battery, currently a hot topic is the catalyst. I mean, catalytic mechanism for lithium sulfur, because lithium sulfur is also a multi-step reaction, involves the liquid or solid phases. So can you give some comments on the development of the, for example, the atomic scale catalyst for lithium sulfur?
Thank you. For the lithium sulfur, because for this usually involve the multi-steps, because the sulfur structure over because it's evolutions, so it is involved the multi-steps, especially for the combinations between the structural evolution and intermediate absorptions between the sulfurs. Overbinding effect is also very important. So this is very important to give the very precise criteria to screen out and classify these candidates between based on just thermodynamic effects. So this lithium migration is another important factors usually need to consider, because lithium is atomically mass is it's just slightly higher than hydrogens. So the migration just throughout this battery is also very obvious. So this is cannot just use the absorption effect to investigate it. So we usually need to use the non-equilibrium models to study the migrations, especially for these dynamics simulations. So this is for lithium migrations. Go back to the absorption effects. The sulfurs usually seldom studied by between all transition metal, lanthanide metals, and main group metals combination, and combined with intermediate absorptions. So this may be open a new route for study these effects, because absorption energies is very important. But only studying the absorption energies not just enough. Sometimes we also need to consider kinetics. So this is very comprehensive factors to consider about that. And also, in certain way, lithium shared similarities with the protons and in electrocatalysts is also needs to be carefully considered. So this is a multi-factors, multi-parameter system project. So give a reference for your consideration.
Okay, thank you. Thank you very much for your comments. Yeah.
Thank you, Zheng Long.